Uh, Welcome to video 2. This is the lecture on Turing Decidability. Last time we saw the notion of Turing machine. It's a little device for computing. It had some simple rules, not unlike that of a deterministic finite automata. It had a little extra power, namely not just moving right, it could also move left. Not just reading the input, but it could also write on the tape on which the input was present, the tape being infinitely long, and right. So reading, writing, and moving in both directions. This is the bulk of it. This was what a Turing machine was. A Turing machine turns out to be extremely powerful, way more powerful than deterministic finite automata. It's as far as we know, it is as powerful as any computing device possible. Uh, but it's certainly as powerful as any modern computer and beyond. It's a mathematical model. It's a simple mathematical model of a computer. Okay. So Turing machines had a quirk which deterministic finite automata didn't have, which is that on an input, sure, sometimes they accept, sometimes they reject, but they may also go into an infinite loop and not halt or not halt ever, meaning they never enter their accept or reject states. They just keep updating their state and keep moving their head around and never enter the accept or reject state. So if they keep doing this, uh, uh, this makes the definition or makes Turing machines a little unpleasant to work with, because every time you take a Turing machine and you feed it an input X and you say, okay, tell me, is X in this language or not? Uh, the Turing machine may start computing, and sure, at some point it may stop and say, yes, X is in the language, or it may say X is not in the language, but it may also just go on forever. And you waiting upon the results of this computation may just be waiting forever. So we need to. So this is a deficiency in, or this is an unpleasant aspect about Turing machines. So to clean that up, we have another notion, uh, just like Turing recognizability. There's the notion of Turing decidability, which is a notion which is much more pleasant for the purposes of asking a Turing machine to solve a problem for you. Okay, so let me remind you of the notion of Turing recognizability. So L, let L be a language in sigma star. L is recognized by a Turing machine M if the set of accepted strings of M equals L. Strings X such that M accepts on input uh, X. We say L is decided by a Turing machine M if on, first of all, L should be the set of strings accepted by M, and second, M should have the guarantee that whenever you feed it any input, it halts. So in other words, it either accepts or rejects. It never goes into the infinite loop setup. So so two things. So L is equal to the set of strings X such that M accepts on input X, and for all y in sigma star, M either accepts or rejects y. In other words, M does not loop, go into an infinite loop. Go on input y. This is the definition of Turing when L is decided by a Turing machine M. And if L is a language for which there is such a Turing machine M that decides it, then L is called decidable, Turing decidable. Otherwise, it's called Turing recognizable in this other case, when L is recognized by Turing machine M's, such that this. Okay. Let me say something obvious. So there's the Turing the Turing decidable languages. The set of all Turing decidable languages. This is a set of languages. So this is a really big set. This is contained in the Turing recognizable languages. And this whole thing in turn is contained in the set of all languages. Which is just the same thing as the power set of sigma star. So Turing decidable languages, it's a special subset of Turing recognizable languages. Oh, it's a subset. It may be equal for all we know right now. And that itself is a subset of all languages. So it's an, okay, so also just for context, let's remember that regular languages are contained in Turing decidable languages. Why? Well, the deterministic finite automaton itself is basically a Turing machine, and we know that it halts on all inputs. So that gives it to you. So let me write here regular languages. The set of all regular languages. Okay. Now we already saw that Turing decidable languages are more general than regular languages. It turns out that the set of all languages is much bigger than the set of Turing recognizable languages. That's this. This is much bigger than this. Why is it much bigger? That's from cardinality. The set of all languages is uncountable. The set of Turing recognizable languages is certainly no more than the size of it is certainly no more than the number of Turing machines. And every Turing machine can be specified by some finite length string or a finite alphabet. And so this set, the set of all Turing recognizable languages, turns out to be countable. So this is uncountable, this is countable. And so this means that there are languages that are not Turing recognizable. The gap between Turing decidable languages and Turing recognizable languages, that's a serious issue. is every language that is Turing recognizable also Turing decidable? Yeah, that's a serious issue. You will hear more about it you will see a complete solution to this in a future lecture. But for now, I'll just say some things. And so we're going to now study Turing decidable languages and Turing recognizable languages. And yeah, we're going to study both of them and the relations between them. And we're going to try to find examples of interesting Turing decidable languages and Turing recognizable languages, yeah, that are useful for further studying of Turing machines. Okay. So, but philosophically, Turing recognizable languages, I mean, for a Turing recognizable language, you may have a Turing machine that recognizes it, but it's not one you would want to call. You would, yeah, or for a normal purpose, because when you call that Turing machine and say, "Okay, tell me, is X in this language or not?" It may not come back to you with an answer. If X is in the language, it will come back to you with an answer, and it will tell you, "Yes, X is in the language." But if X is not in the language, it may just run on forever, and it may not come back and say it's not in the language. So the definition of Turing decidable languages fixes that. It fixes that by saying, oh, we are interested in Turing machines which have the extra property that on every input, they always halt and tell you an answer, either accept or reject. Going to this more sophisticated notion of Turing decidable came at a cost. It's not easy to tell, or it's not obvious, when a Turing machine has this extra always halting property. So let's go back to the definition. We had in the definition of Turing decidable, uh, we had, okay, first of all, L had to be the set of strings accepted by M, but we also had this extra condition, which is about every single Y in sigma star. If I give you a Turing machine, it's not clear to, or if you give me a Turing machine, it's not clear to me how I would check that no matter which input you feed this Turing machine, it halts. Then, when a Turing machine is allowed to have a have an arbitrarily complicated looking uh, set of states and transition function, etc., it's not clear how to look at it and say, oh, this Turing machine never goes into an infinite loop. It's related to the problem of, so I mean, I said it in terms of Turing machine, but an almost equivalent version is, you give me a program written in C and I have to tell you, could this ever go into an infinite loop on some input? Okay, so that's not easy. I mean, people try to solve this in uh, I mean, in software verification and things like this, but in this full generality, with when people write adversarial programs, or people write arbitrary programs without uh, yeah, when people write complicated programs, not trying to make it easy for you to decide whether it's doesn't have an infinite loop or not, trying to tell whether there's an infinite loop or not is not obvious at all. Okay, so good. So closely related, so I'm going to define two slightly related notions, uh, and we'll see that uh, enumerability, well, we'll talk about the notion of enumerability, which is something that Turing recognizable languages have. Okay, so enumerability.